So in the last talk, we looked at creation from a biblical perspective. Now we're going to talk about creation from a scientific perspective, and particularly from the perspective of physics and astronomy. And so we're going to be looking at creation and the Big Bang. So Genesis does not tell me the scientific details about how the universe began. So what does astronomy and physics say? Well, why do scientists believe that the universe is 13.79 billion years ago? And how is our universe unique? And why do some scientists support the idea of a multiverse? So we're going to look at that in this lecture and the next one. So basically, that what science tells us, many years of research, is the universe, both time and space, had a beginning. And this beginning was 13.79 billion years ago. But it's important to make some qualifications about what this means. The first is that the Big Bang theory and the data from astronomy that support it says nothing about the origin of the ultimate origin of or cause of the beginning, or what existed before it. And second, any alternative scientific theory of the history of the universe must give a quantitative description of all of the available data. So let's now look at the science. So when we talk about cosmology, when we say cosmology, it's the cosmos, and particularly what the history of the cosmos is. It's about the whole universe, not just the Earth, the solar system, or a galaxy, but the whole universe. And there's two basic pillars or assumptions that come into this scientific field. The first one is Einstein's general theory of relativity, which was developed in 1915, more than 100 years ago. This theory goes beyond Newton's theory of gravity and can describe both weak gravity and strong gravity. And it's summarized in one single mathematical equation. And this equation is shown here. Now, you don't need to understand it. I realize it's just maybe just Greek to most of you, but it makes a connection, a mathematical connection between mass and matter and the curvature of space-time. So this was Einstein's theory. And then it's important to know that it makes very specific mathematical predictions about what you should observe in the laboratory and in astronomy. And there's been many tests of it, and they all are consistent with Einstein's theory. So we have a lot of confidence that it's correct. But we want to apply the theory to the whole universe. And so to do this, we adopt what's called the cosmological principle. Now, this is the assumption that the universe is the same everywhere and in all directions. So we say it's homogeneous and isotropic. Now, this is an assumption, but there's significant data that is consistent of this. And so if we look at this picture just above my head, that is a big picture of all the galaxies in the universe. And what you might notice is it looks very uniform and it looks the same in all directions. And so this assumption then is reasonable. And I stress this is looking at things on a very large scale, on the scale of like millions of light years, because it's obvious that things are a little bit clumpy. If in this room, there's matter in some places, but not in other places. And then if we look at the whole Earth, there's matter not distributed evenly, and similarly in the solar system or the galaxy. But if we look on a very long scale and smooth things out, it is very uniform. And so we take these two principles and then we see what the theory would predict. And one of the surprising things is that the theory actually predicts the beginning of the universe. And this was a surprise. So Friedman, a Russian mathematician, he solved Einstein's mathematical equations for a uniform isotropic universe. And this was done about 100 years ago. But it was never taken too seriously. But in 1927, George Lemaitre, a Catholic priest and physicist, he proposed that it should be taken seriously and that there was a beginning to the universe. Now, Einstein himself rejected this solution as unphysical because he considered that, as far as we knew, the universe had existed forever. And so in order, though, to maintain this idea that the universe was the same forever, he modified his equations, and he introduced something called the cosmological constant in order to get a static universe. Later, he realized this was a mistake for reasons we'll see, and he called this his greatest blunder. Now, originally, though, this theory of the beginning of the universe was still not taken that seriously, and there were alternatives. And so there was an alternative to the Big Bang, and that was called the steady state universe. This was proposed by Hermann Bondi and Gold in 1948. Now, this was vigorously supported by a very prominent astronomer, Fred Hoyle. He was an atheist, and he supported this on philosophical grounds. And you see here, this is a quotation from a scientific paper in a scientific journal where he said, "This possibility, the steady state model, seemed attractive, especially taken in conjunction with aesthetic objections to the creation of the universe in the remote past. For it seems against the spirit of scientific inquiry to regard observable effects as arising from causes unknown to science, and this is in principle what creation in the past implies." So this was an alternative model, and for a while it was consistent with the data, but eventually it wasn't. So let's come to that. What is the evidence for the Big Bang, the idea that there's a beginning to the universe? Well, there are three independent lines of evidence which give support for the Big Bang model, for a specific Big Bang model, but it's also, these are quantitative. So it's not just qualitative agreement with the theory, it's quantitative. Now, the three independent lines of evidence, which we'll look at briefly, are, first of all, the expansion of the universe. Second is the cosmic microwave background radiation. And third is the relative abundance of chemical elements. And I'll explain now what these three are. And the last 30 years have produced massive amounts of observational data that rule out many other alternative models, including the steady state model. And all of the data available now is consistent with the universe being 13.79 billion years ago. So let's see why that is. So first of all, we'll go back to the Friedman's solution of Einstein's equations. Now, what these solutions do is they can produce a graph that tells us how the size of the universe has changed with time. And so there are actually 4 different, qualitatively different curves. And so if we are sitting here now, we can look at what the theory predicts will happen in the future and what has happened in the past. Now, the common thing you see is these are different parameters in the theory. There's 4 different curves corresponding to different densities of matter in the universe, and also different amounts of dark energy, which is related to the cosmological constant. Now, the common thing as you go backwards in time is that they all go to 0. And so that's telling us that they all predict that in the past there was a beginning, that in a sense there was no universe. It was like the size of an atom. But then they also make predictions. One predicts that actually the universe will collapse in on itself, and that's because there's so much mass and high density gravity will cause it to collapse. But if it could expand steadily forever, and it could even be accelerating. So why would we believe that this would be true? And how can we compare these curves to what is observed? Well, the first thing is that we do observe expansion of the universe. This was discovered by the American astronomer Edwin Hubble in 1929. Now, what Hubble observed was that every galaxy he looked at, he saw was moving away from us. And the speed at which they were moving was proportional to the distance involved. So I'll give a little analogy to explain what's happening. And one thing you might wonder is, well, why are all the galaxies moving away from us? Doesn't that suggest that, you might think that suggests that actually we're the center? But no, it's not true, because of that. It's actually all of space is expanding. So take this analogy. Suppose I want to make a cake, and I put some currants or raisins, little pieces of fruit inside the cake, and this is the dough. And then I put yeast in it, and it rises and expands. Well, it doesn't matter where I sit in the cake. What I see is that all the points in the cake are moving away. So it doesn't matter if I'm sitting here or there, I see everything moving away from me. And so this is the way that actually is what is happening in the universe. But if we can measure how fast it's moving away, things are moving away from us, and we can measure that distance, we can then extrapolate backwards to when everything was on top of each other, and that allows us to estimate the age of the universe. And when we do that with careful mathematics, we'll end up with this same time of 11.79 billion years ago. So that's one line of evidence. But, maybe there's another interpretation. But turns out there's 2 more lines of evidence. So the second line of evidence is something called the cosmic microwave background radiation. So let me explain what that is. So this is something that was predicted by physicist George Gamow in 1948. And what it is that if suppose there was a Big Bang, then there was a time when the universe was very small and highly dense, and then there would have been a lot of heat generated, and then as the universe expanded, that heat would spread out. Now, if it was hot enough, that would produce radiation. It's just like when you look in an oven and you see the red, hot elements. So it's producing visible radiation and a lot of infrared radiation. And then as you open the door of the oven, all that heat inside expands out, and then so will the infrared radiation. Now, this again was not observed until 1965, when it was actually discovered by accident by two radio astronomers in New Jersey in the USA. And you can see here a picture of their radio antenna, and you might see down there's two relatively small men there. But they found this hissing in their scientific instruments, and they thought it was noise, and then they thought it was pigeon droppings inside the telescope, the radio telescope, but turned out to be the cosmic microwave background. Now, what you also see when you do much more precise measurements of this radiation, it's extremely uniform and isotropic. Wherever you look in the universe, it's basically the same. And you can measure its temperature, the temperature of the radiation, which is microwaves, very accurately. And here you see it's 2.7255 degrees Kelvin, and this is Kelvin, this is near, so it's near absolute zero. This is minus 270 degrees centigrade. So it's very cold. But you can also find small fluctuations in that temperature. And you can see here on this map of what it looks like in different variations, very small variations. And that is also predicted by the Big Bang model. So in 1965, basically this led to the rejection of the steady state model because it could not explain the existence of this radiation, whereas the Big Bang model could both explain it, that existed, and also what its temperature was and why it was so uniform. So the expansion of the universe, cosmic microwave radiation, we have two independent lines of evidence, and both of them can be used to predict the age of the universe, and you end up with the same number. But this is not the only line of evidence. There's another line of evidence, and this is the relative abundance of nuclear isotopes. So if we look at the universe, we look at different stars, we can determine what their chemical composition is, how much hydrogen they have, helium, lithium, magnesium, other elements that are found in stars. But there are also what are called nuclear isotopes, which are like helium-3 and deuterium. So deuterium is where you have one proton and one neutron together, and helium-3 is where you have two protons and two neutrons, whereas in common helium you'd have two protons and two neutrons. Now the basic idea was that the early universe was hot and dense, and then rapid expansion led to cooling. And after 3 minutes, the chemical elements started to form. And particularly, you now had not just hydrogen, but then hydrogen atoms could combine, or protons could combine to produce helium and deuterium and lithium. So these light elements were made in the very early universe. Now, a question is, well, how much how much would you end up with these different elements? Well, that depends on the laws of nuclear physics. And so if we take the laws of nuclear physics that we've discovered on Earth and we just assume that they're also going to be valid at very high densities and high temperatures, using mathematics, you can calculate how much you should have of these different elements. And what you find is that then the amount of these elements depends on the density of the universe at that first 3 minutes, and also when that was happening. And then you can compare that to what you observe in terms of the relative amounts of helium and lithium, deuterium. And this is a graph of how those things would vary with density. And from that, you can work backwards then to work out the parameters of the Big Bang, including the age, but also the density of the universe. So with these 3 independent lines of evidence, we can determine not just that there was a Big Bang, but many details about it. And so this is a summary of just what you learn. Now, one is that we talked about the universe expanding or contracting, and it doesn't contract, and that would be if it had a spatial curvature, but the universe is spatially flat, and it will expand forever, and it is also accelerating. And the cosmological constant is non-zero. But then we'll come to how there's a lot of fine-tuning involved and what that means. But also it tells us what the composition of the universe is. And it tells us that only about 4.6% of the universe is made of atoms, that what we're familiar with, what we're made of, and what tables and chairs are made of. Whereas a quarter of the universe is something called dark matter. This is rather strange. It's basically some substance which involves that will experience the forces of gravity, but you can never see it, and you can deduce it exists because of the effect it has on the movement of galaxies and things. But then even stranger is something called dark energy, and that's associated with the cosmological constant. And what dark energy is and dark matter, these are outstanding research questions. But the data is clear that they must exist. Now, if you want to know more, this is a nice book, Big Bang God, A Universe Designed for Life, written by Reverend Dr. Rodney Holder, and it explores in more details some of these questions. It is in the SciEx library if you ever get to visit on campus. And so we'll wrap things up there before we move on to talk about these important questions of what is fine-tuning and why do some scientists believe in the multiverse.